All right, let's jump right into this. Welcome to today's Explainer, where we're going to be focusing on an absolutely massive fundamental breakthrough in audio artificial intelligence. We're looking at a brand new model called MiMo-Audio, and we're going to unpack what researchers are literally calling the GPT-3 moment for the speech domain. Now, I want to be clear right up front. This isn't just some minor incremental software update. What we're talking about today is a complete paradigm shift in how machines actually understand and generate human language. To really grasp why this is such a huge deal, I want you to just imagine something for a second. Think about how effortlessly you switch from, say, whispering in a super quiet library to suddenly raising your voice to make a point in a loud debate, or how you automatically slow down and change your tone when you're trying to explain a complex math problem to a child. How do you actually do that? Well, you obviously don't have to download a new software update for your brain, right? You just adapt effortlessly based on context, your emotion, and your environment. But notice the stark contrast here. When we look at traditional AI, human adaptation requires just a tiny bit of context to instantly change tone or style. Traditional AI, on the other hand, is incredibly rigid. Historically, if you wanted an audio model to, let's say, translate a language, you had to train it specifically for translation. If you wanted it to transfer a specific vocal style, well, you had to go in and manually fine-tune it just for style transfer. These older models completely stumble the second you ask them to do something outside their very narrow, specific training. They basically require constant, heavy micromanagement to do anything useful. So how do we actually fix this? Well, here is our roadmap for the Explainer today, so we can build this concept from the ground up. We'll cover 1. The audio intelligence problem. 2. The GPT-3 audio moment. 3. How MiMo-Audio works. 4. Real-world speech tasks. 5. Translating the results. And finally, number 6. Impact and limitations. Okay, let's dive straight into section 1, the audio intelligence problem, and exactly why speech AI usually stumbles. So the really crucial thing to remember here is that speech is not just text read aloud. It contains what we call paralinguistic information. That means your emotion, your breathing, your specific tone, the acoustic environment you're in, the whole shebang. Traditional models generally just strip all of this rich, layered information away. They convert the audio into text, they process that text, and then they convert it back to audio. And when you do that, you essentially lose the soul of the speech. Because they lose these crucial acoustic details, they just cannot natively understand emotion or environment without being heavily fine-tuned for every single specific task. Which brings us to section 2. The GPT-3 audio moment, and how researchers are scaling up to fix this. To crack this problem, the researchers took their pre-training data and scaled it up to a massive 100 million hours of audio. Just to put that number into perspective for a second, that is an entire order of magnitude larger than the data used for previous open-source speech models. They fed this model everything: public podcasts, audiobooks, news broadcasts, political debates, you name it. And by scaling up to this extreme level without losing all those acoustic details we just talked about, they were aiming for something very specific. They were aiming for what's called emergent behavior. Now, if you haven't heard this term, it happens when an AI system is trained on just massive amounts of data, and it suddenly and spontaneously learns how to perform completely new tasks that it was never specifically programmed to do. Think of it like this. It's kind of like a 15-year-old who reads so many different books across so many different genres that one day they just suddenly know how to write a brilliant stage play without ever taking a single playwriting class in their life. The sheer volume of data actually unlocks brand new atomic skills. And you can see exactly when that happens right here. Notice the x-axis showing the training tokens. The model's accuracy on these really complex tasks is essentially flat, right? Hovering near 0. It basically couldn't do the tasks at all. But then, right around the 0.7 trillion token mark, look at that massive spike. The model just suddenly woke up. Performance completely skyrockets and then stabilizes. It didn't slowly, gradually get better over time. It underwent a literal phase transition where it suddenly understood how to perform few-shot learning, meaning it could now learn completely new speech tasks from just a handful of examples. So how is this happening under the hood? Let's go to section 3, how MiMo-Audio works. Looking at the pipeline. The architecture pipeline really boils down to four main steps. First up, the MiMo-Audio tokenizer takes the raw audio and turns it into high-fidelity tokens. This makes sure it captures both the meaning of the words and the acoustics. Second is the patch encoder, and this step is absolutely vital. Audio data is huge and it comes in fast. The patch encoder downsamples it. It effectively chunks a fast-spoken sentence into slower, digestible patches, almost like syllables, for the AI to process without getting overwhelmed. Third, we hit the large language model. This is the brain that natively processes these interleaved audio and text patches. And finally, step 4, the patch decoder reconstructs all this data back into high-fidelity audio output. And looking at the actual schematic for this pipeline, I really want you to notice how seamlessly the audio and text interleave within this unified system. You can clearly see the patch encoder aggregating the audio frames, and then it feeds them directly into the MIMO 7B language model right alongside the text, and then out through the patch decoders. There is no clunky translation layer in the middle stripping away the emotion. The model is literally thinking in both audio and text at the exact same time. All right, moving to section 4. Real-world speech tasks. Let's see what it can actually do. When we compare these approaches on real problems, the leap forward is pretty obvious. Take voice conversion. Traditional AI required you to train a whole new voice model from scratch. But with MiMo, you literally just give it a few audio examples and a prompt, and it instantly mimics the timbre. What about emotion conversion? Traditional AI relied on this really stiff, rigid mapping. MiMo just uses a few examples to adapt the tone naturally, on the fly. And for speech translation, traditional AI needed a massive multi-step pipeline, converting speech to text, translating the text, and then synthesizing new speech. MiMo just bypasses all of that. You give it a few examples, and it performs direct speech-to-speech translation. It's generalizing tasks on the fly, honestly, a lot like a human does. Let's look at the hard data in section 5, translating the results and beating the benchmarks. So, if we look at the MMA-U benchmark, which tests general audio understanding, meaning speech, sound effects, and music, MiMo-Audio just dominates with an overall score of 74.9. As you can see, it comfortably beats other leading open-source models like Step Audio 2, which scored 72.7, and MiMo-Audio down at 68.2. This proves that scaling up that lossless audio data we talked about earlier directly translates to a fundamentally superior understanding of the acoustic world. But it goes way beyond just general audio. To test its actual reasoning capabilities, they use speech MMLU. These are massive, highly complex, university-level exams, but delivered entirely in spoken audio, and MiMo scored an unprecedented 69.1 on these speech-to-speech evaluations. It outperformed its competitors by huge margins, proving this incredibly high level of speech intelligence. It can actually listen to a complex academic question, reason through the logic natively in its own brain, and then speak the correct answer back to you. Finally, let's wrap things up with section 6, impact and limitations, getting the full picture. Because in the interest of fairness, it is definitely crucial to note the model's current limitations. No model is perfect, right? While it's a massive leap forward, it definitely still trips up. For example, it struggles with generating speech when there's complex background music playing. It also tends to mispronounce complex mathematical symbols and formulas. Also, during really long spoken dialogues, its style control can get a bit unstable, which causes the voice to weirdly shift mid-sentence. And finally, when it's utilizing its thinking or chain of thought mechanisms for music understanding, it does sometimes hallucinate incorrect information. But honestly, even despite those limitations, the paradigm shift here is completely undeniable. As the researchers themselves state, this is a GPT-3 moment for the speech domain, bridging the gap between perception and complex cognitive tasks. We are finally moving past those rigid, task-specific models of the past into an era of truly general, intelligent audio processing. The machine isn't just hearing anymore, it's genuinely understanding. Which leaves us with this final, kind of wild thought to chew on. If AI can now adapt its voice, instantly shift its emotion, and reason through complex problems as effortlessly as a human, what exactly happens when these highly capable models start having real-time, unstructured conversations with each other? We are stepping into a very, very fascinating future. Thank you so much for joining me on this explainer, and keep learning.